So if we look at this script, what we can see is that we've run a simple DFT calculation and we've run a LDA calculation. Okay. What we haven't set up, what we haven't defined, is what kind of exchange correlation functional we want to run. It's just automatically chosen LDA, right? And we also haven't determined things like how many frequencies we have in our plane wave basis, right? So obviously we're doing a plane wave basis because we're running a cast-up calculation, which is a plane wave code, but we don't know how many frequencies we're containing, how many frequencies we have in our basis set, right? So when we talk about a plane wave basis set, what we really, the parameter that we're talking about is the plane wave cutoff energy, or the kinetic energy cutoff, right? And so this is usually determined in EV or Rydberg, depending on the code, right? So in cast-up we usually use EV, and people will say the basis was 300 EV or 500 EV or 1000 EV, okay? And all this tells us is how many frequencies we have in our basis, okay? 1000 EV has more high frequency than 500 EV, okay? The higher the number, the better the basis, okay? So the first question to ask is, what frequency do we need to, sorry, what maximum frequency do we need to use? So what we can have a look at is the pseudopotential, right? So if we look at the pseudopotential of palladium here, what we can see is there's some suggestions for a palladium calculation, right? These are in EV, in the palladium pseudopotential, from about 400 to 800 EV, okay? So if we ask for a coarse or a medium or a fine basis, what it's going to do is it's going to choose in EV the basis in that table. Okay. Right. So we can do that. Let's try it. So what I want to do here is I want to say my calculator. Okay. I can say calc dot, and now I can change some parameters. So param dot, and what I want to do is I want to change the cutoff energy, right? So I can say cutoff energy equals, and I can say some number in EV, right? So I could say, for example, 600 EV, right? Or I can leave off the EV because it's a default unit, right? Or I can say calc dot param dot, and I can say, because I want to make my calculation simpler for myself, and I know that cast-up knows what is coarse, what is medium, and what is fine. I can say basis precision equals, and I can set that to be, for example, fine, right? If I set the basis precision to be fine, right, what's happening now is in my input file, I'm going to set fine, and it's going to automatically choose 490 EV. If I set basis precision extreme, it will choose 784 EV. Okay? And you might ask, all right, well, what happens if I do palladium oxide? What happens if I have two different species in my calculation, not just palladium? Well, in that case, we'll have two pseudopotentials, one for palladium, one for oxygen. And if I ask for fine, it will go to both oxygen and palladium, and it will find the fine cutoff for oxygen and palladium, and it will choose the highest cutoff for the whole calculation for palladium oxide. Okay? Next thing to address is, well, what does fine mean, right? And the way these are determined is quite simply by asking, if I do a calculation of a single atom, right? So for example, a palladium atom, right? If I want my accuracy to be lower than 10 to the minus 3 EV, I think, no, sorry, 10 to the minus 5 EV in accuracy, then it's fine. Okay, so this is all in the CASTEP manual, right? Fine, extreme, medium, they just represent accurate. They represent the threshold in accuracy for a single atom species calculation. All right, so that sets basis precision to be something specific, right? But also I want to set my exchange correlation functional to be something specific. We know that it's doing LDA, but it's chosen LDA just by default. Okay, so what I really want is to be able to say param.xc functional equals, and I want to set it equal to something. So I could set it equal to LDA, right? And if I set it equal to LDA, I know that I'm doing an LDA calculation. On the other hand, if I set it equal to PBE, right, I know that I'm doing a PBE calculation. What is a PBE calculation? A PBE calculation is a GGA exchange correlation functional, right? So if I run that again, it will run a PBE calculation with a fine basis set precision, and the fine basis set precision is about 500 EV. Okay, I'm going to rename it. I'm going to call it PBE or Palladium PBE. Right. So if I run that again, right, wait a couple of seconds. Right, what we can see is now we have a new directory, Palladium PBE. Right. If I go to the command line, and I go into PD PBE and PD PBE, and I tail the output of PBE.castep, what we can see is now at the beginning it ran a calculation very similar. Now it's finished. Right, and we can load that calculation in here, and what we can see is that it generated a pseudopotential calculation. Right, it did a pseudopotential calculation, and what we should be able to see is that it's doing a PBE calculation. Right, over here you can see that it's a PBE pseudopotential. Right, so we asked for a PBE calculation, and we can also see if we go down a little that we asked for a fine basis set precision. So at some point, right, we see we're doing 490 EV as our basis, right, 490 EV. And so the 490 EV PBE calculation, go back into the Jupyter notebook and we type in energy. What we should be able to see is that our energy is actually very similar to our LDA energy overall, but actually is also very, very different. Okay, so the number of the EV difference between the LDA and the PBE calculation is about what? Well, approximately 10 EV different, and that's actually quite a big difference in energy. Okay. The next thing we need to bear in mind when we're doing a DFT calculation is a DFT calculation on a crystal is, what about our Brillouin zone sampling? What about our K-point sampling? Okay, so we know that we need to consider the block waves, and we need to sample over K-points. Okay, so the first thing to ask is our calculation already sampled over the Brillouin zone? Okay. And if we go back into our CASTEP calculation, where is it? Here. Oh, PBE, this one. If we go back into here, and we go up a little, what you can see is that we have K-points for Brillouin zone sampling. So once again, CASTEP has guessed how many K-points to use, right? So it says it's doing a Monkhorst pack grid for the SCF calculation of 3 by 3 by 3. Okay, so basically, it's taking our Brillouin zone and it's got three dimensions, and it's sampling 1, 2, 3, 1, 2, 3, 1, 2, 3, and we have a 3 by 3 by 3 grid sampling of the Brillouin zone. Okay. Question is 3 by 3 by 3 good enough? Okay. At the moment, we don't know whether it's good enough. Okay. So what we can do is we can just once again copy this cell, right? Paste the cell, and we can say, well, what I'm going to do now is I'm going to say k points MP spacing equals, and I'm going to set the spacing to be some number. Okay. Or I can set k point MP grid equals some spacing like 4 by 4 by 4. Right. Another trick, at least with castep, that you can do here. So if I type castep.mpi and I type help search kp, right? What you should be able to see here k point MP grid, right, as you can see, it tells us the name of this keyword, right? So if I don't search, but I instead just type k point MP grid, it tells us what we can type, right? So castep has a built-in search feature. Right, so let's enter k point MP grid equals 4 by 4 by 4. Right, let's try running that calculation. But right now I have a pretty bad headache, right? So it's little difficult. Today's just going a bit badly, right? Hopefully tomorrow will be better. Anyway, right. What we have to do in order to decide that our calculation is good enough is we have to choose an exchange correlation functional, so LDA or PBE, and we have to choose a basis, right? So a cutoff energy, and we need to choose a Brillouin zone sampling. In this case, 4 by 4 by 4, right? So what you can do to check this for yourself is you can do a calculation, right? You can do a calculation. You can just copy and paste this several times, or if you know how to use Python, you can run a loop, okay? And what you can do is you can, for example, I can change it to be, right? I can run a calculation at 500 EV, then I can run the next calculation, 500 EV, then I can run the calculation at 600 EV, 700 EV, 800 EV, right? And each time I can look at the energy, right? And for example, in this case, I can change this, the name of this to be energy 500, right? And then the next one, I can change it to be energy 600, right? And I can print out energy 500, energy 600, energy 700, energy 800, right? And what you want to see is something like that, right? You want your total energy to converge. You want it to go flat, right? So at that point, what you can say maybe that's, I don't know, 700 EV or 500 EV, right? At that point, you can say my energy has converged, and this is a good enough basis, 700 EV. Okay, so if you do exactly the same calculation at say 400 EV, 500 EV, 600 EV, what you're getting is 400 EV, 500 EV, 600 EV. So this is the cutoff, and this is the total energy. Right? And once it's not changing, you can say this cutoff, which in this case 700 EV, is good enough. 700 EV. right? Right. You can also do the same thing with the Brillouin zone. Okay? You can do the same thing with the Brillouin zone. So once you've decided, okay, I'm going to do 600 EV, or I'm going to do 700 EV, whatever you've chosen as your cutoff, right? You can also do a convergence test in the Brillouin zone. Okay? So in the Brillouin zone, now what I want to do is I want to look at gamma point. So this is 1 K point. 2 by 2 by 2. I'm going to label that 2. 3 by 3 by 3. 3, 4, 5, etc. Right? And along this axis is going to be my energy. Total energy. Right? What you will find, or what you should find in this case, is I get a total energy for a gamma point calculation. Okay? We know that we do not include enough of the block waves in this case, right? So the 2 by 2 by 2 is going to be different, right? However, what you will find that's different compared to the cutoff energy convergence case is that this is not going to be a monotonic convergence, right? Instead, we're going to get something more like this. Right? Something a bit more like that. Okay, and the reason is because we've got uneven sampling, odd even sampling. Right? In the case of gamma point and 3 and odd, so 1, 3, 5, we're including the gamma point, the 0 point. Right? In the case of even, we are avoiding the gamma point, the middle point of the Brillouin zone. Right? So actually what's going on is the convergence for the odd sampling is monotonic, right? And the convergence for the odd sampling looks like that, okay? But what you'll notice is eventually it still converges, okay? But is it going to be 5 by 5 by 5, 6 by 6 by 6? We don't know, okay? And so what I mean by that is once you've chosen a cutoff, say 600, add, all right, what I can do, so I've chosen my cutoff is going to be 600, I said 700, right? So 700, this is my cutoff. And now I need to run, say, 4 by 4 by 4, 4, 4, 4, right? And I need to run again, another one, 5 by 5 by 5, 5 by 5 by 5, 5, 5, 5. And so I'll run the calculations 1 by 1 by 1, 2 by 2 by 2, 3 by 3 by 3, 4 by 4 by 4, 5 by 5 by 5. And what I will get is a graph a bit like that. Okay? Right? And this will tell you how I can get the best possible calculation, which is converge with respect to my basis, my cutoff energy, and converge with respect to the Brillouin zone sampling. Right? So why don't you try that? Right? So if you log on to the system and you try this, what I will give you is this. Right? So in fact, what I will give you is a gamma point calculation. Right? Gamma point calculation, you need to converge this. 1 by 1 by 1 is not good enough. Right? 2 by 2 by 2 is not good enough. 3 by 3 by 3 is not good enough. You probably need something like at least 5 by 5 by 5, is my guess. Okay? Cutoff energy, we can start at 300, right? And maybe it's your choice what you want to do. You might want to do 350, 400, 450, 500, or you might want to do every 100. You might want to do 300, 400, 500, okay? But you can do it. So what you can call your energies, I don't know, 600, 111, right? you can call them whatever you want, right? It's your choice what you name your variables, okay? But you can take that and you can try running, what did we say, 300, sorry. You can try increasing the cutoff energy and increasing the Brillouin zone sampling, right? So if I take that and I copy that and I put it into here, and you can try running some of those calculations, right? And I'll also paste this, which you can use for viewing the your calculations. And one final thing before you start running some calculations yourself is, you can imagine if you run 300, 400, 500, 600, 700, 800, okay, 700 is good enough. Now I'm going to run 700, I'm going to run 1 by 1 by 1, 2 by 2 by 2, 3 by 3 by 4, whatever, right? You're going to have to run all of these calculations over and over and over again. It's going to get quite messy, right? Because this is all in Python, if you choose to, you can run everything in a loop, right? So if I wanted to, I could just do, for instance, I'll just do the example of the cutoff energy. What I could do is I could say for I in range n, right? And I'm going to say I'm going to run n calculations. N is going to be 6, right? I'm going to run 6 calculations, right? So what's going to happen is every time in my loop, I need to make a new cutoff energy, right? So I'm going to start at 300. So I'm going to say my cutoff equals 300 plus I times 100, right? So I'm going to start at 300 because in Python, my range starts from 0, right? So I'm going to start at 300, and then I'm going to do I times 100. So the next time it's going to be 100, right? 100 plus 300 is going to be 400. And then I'm going to have I is going to be 2. So I'm going to have 100 times 2, 200 plus 300 is going to be 500. So it's going to be 300, 400, 500, 600, 700, right? 800. All right, so that's going to be my cutoff. And all I need to do here, so I'm going to maybe start with a cutoff, a k-point grid of maybe 2 by 2 by 2, I don't know. And I'm going to have my cutoff energy is going to be calc equals cutoff, like that, right? And then when I run the calculation, energy, whatever, right? It's going to run that calculation for 300, 400, 500, and then I don't need to do them manually each time. I can just run the loop, and it will change the cutoff energy and run each of them individually for me. All right. So if I want that to go into a form that I can easily plot, I can put it into memory. I can say, let's say cutoffs equals some list in Python. And if I want to say my energies equals some list in Python, all I want to do once I've done this calculation, this is my cutoff value. So I'm going to say cutoffs dot append cutoff, and my energies dot append energy, right? And that will store in memory each cutoff that I use. So the x-axis points, and for each x-axis point, it will also store the energy value that we calculate in Castab. Right. Let's see whether I've made any mistakes in that. Also, it might be nice to just print out. Oops. It might be nice to just print out the cutoff and the energy that we get at each point, and maybe also we'll also print out I plus 1. Okay. Right. So if we run that, let's see what happens. Right. So we got a calculation running, and then it had a problem on the second. What have I done wrong here? I think I should put another underscore in cutoff energy. Right. Let's run that again and see what happens. Just a second. Right, so we can see our 300 EV. So that's that point. All right, let's just let it run the second one to make sure that it's working. Right, and then 400 EV. So we get that point, that point, that point. And what we should see is that we've got a difference between 300 and 400 EV, quite a big difference, right? And as we increase our basis, that difference should grow smaller. Okay, it should go flat. Okay. So what I'm going to do now is I'm going to put that script also in the group if you want to use it. So you can do it this way, or you can do it manually yourself. Just run each calculation individually, or you can run a script and you can loop. Your choice, right? So what I ask you to do now is to try running that. Maybe try a different metal, right? You don't have to do palladium. You could do platinum. You could do copper. You could do anything you want, right? It doesn't have to be platinum. But try running some calculations. See if you can converge the basis and the Brillouin zone sampler, right? And that's your homework, right? So you can start it now and run these calculations. So all I want you to do is to try it, right? If it doesn't work or you have problems, work together if you want. I don't mind, right? This class is not about giving you exams and trying to find out who's the best and who can do it and who can't do it. The question is just to try to learn in a useful way, right? So if you want to work on your own and if you want to do it entirely your own way, you don't want to do it like I did it, that's fine. If you want to do it exactly like I did it, but you just want to change the metal, that's fine. If you want to work together with somebody else, that's fine. Do whatever you want, but just try it, okay? Do a convergence test in energy convergence and Brillouin zone, and yeah, that's it. So I think I'm probably going to go now because I think I need to go and sleep. And so hopefully my headache's going to go away, and I'll come back tomorrow and we can do some more stuff. Okay? If you have any problems, send me a message. I think I'll be awake again in a few hours. And so if you have any problems, I can send you a message, or you can come to the office and we can talk about it and we can do some calculations later. Or we can just look at it tomorrow. Your choice. Okay? But anyway, it's almost the end anyway. I think we're just going to end maybe 5 minutes late. 5 minutes early.